Right, let's have a look at atom economy. And first of all, you might ask, where does this term even come from? Well, it comes from the 12 principles of green chemistry, which were set up, I think, or first discussed in 1998, and set up as a bit of a framework to try and design processes and chemicals that were more green or environmentally friendly, more sustainable, and so on. And number 2 of those 12 principles states something like design or try to design processes where as much of the starting materials as possible end up in the desired product. So effectively what that's saying is we need to try and maximize efficiency by minimizing the waste products that we produce in a chemical reaction. So in order to understand this concept and work out how to calculate it, let's take a bit of an analogy using some Lego. So here is a process with Lego. I'm starting with a Lego plane and I want to try and build a Lego car, and we find that there are some leftover Lego bricks as well. So the first thing to note, my starting materials is going to be my Lego plane, and the desired product in this case is going to be my Lego car. And obviously, shown in the kind of equation type thing here, we've also got some waste product or some leftover Lego bricks as well. So let's stick some numbers in there. Let's imagine my plane contains 75 Lego bricks. My car actually only uses up 51 of those Lego bricks, and we're left over with 14 Lego bricks. So in this case, to work out, let's call it the Lego economy, what I'm going to do is I'm going to use the following equation. And it's simply going to give me the ratio of bricks in my desired product, which is 51, divided by the bricks in my starting materials, which was 65, and then to make it a percentage, we're going to multiply that by 100. So sticking those numbers into that formula, we end up with something that looks like that, and we get a Lego economy of 78%. And what does that 78% mean? Well, it means 78% of the bricks in my starting materials were used in my desired product, which actually indicates that 22% of those bricks were actually waste products or not needed in my desired product. So that's a reasonably efficient process. Now, if we apply that process or that analogy to an actual chemical process, let's take a chemical reaction, something like this, where I've got dibromoethane, which is my starting material. Of course, in chemistry, starting materials we call reactants. My desired product is the first of the products, that's bromoethane, which is used for a number, in fact, it's bromoethene, used for things like polymers. And you'll notice there's one waste product there as well, which is the hydrogen bromide. So now using a very similar formula to calculate atom economy, and this is found in the data booklet. Obviously we're not dealing with Lego bricks this time, so we're trying to think about the atoms, and what we're actually going to use is the molar mass instead of the number of Lego bricks. So it's pretty much the same formula. I take the molar mass of my desired product, divide it by the molar mass of all of my reactants. In this case there's only one reactant. Multiply it by 100 to turn it into a percent. So finding those molar mass values from the periodic table in the data booklet, I'd end up with something like this. And if I do that calculation to the end, we end up with a percentage atom economy of 56.931. Now in this case I've been consistent with my significant figures in the final answer there, which is 5, because the two numbers I got from my data booklet also have 5 significant figures. If a question asks you to use less significant figures, by all means do so, but if in doubt, use the same number as the data that you are using in the calculation. So one thing to note, if for example I happen to have some stoichiometric coefficients in my balanced equation, let's imagine there was a big 2 there, that 2 would have to be included when calculating the molar mass. So in that case I would have to have 2 times the molar mass of dibromoethane when I put it into my formula. So it's a very brief summary of what's going on there. We have talked about atom economy, which is simply a measure of efficiency, specifically related to the principles of green chemistry. If I have a high atom economy, it means I have low wastage in my process, which is a good thing. And vice versa, if I have a low atom economy, I have high wastage, which is undesirable. And that's pretty much it for atom economy. Hopefully this video was of some help.